So today we're going to start looking at thermographic inspection as the next module. And here. So thermographic inspection, I guess I'll give you the quick before I go to the next slide. Thermographic inspection is basically we're going to look at the heat being emitted from an object. And I use the word emitted as a key word here. And we'll look at what that means in just a minute. But thermography was developed primarily for composite structures. Composite structures pose a lot of challenges with other more traditional means of non-destructive testing. Obviously, they can't be used with things like magnetic particle inspection or eddy current testing, or dye penetrant for that matter, because the fibers will soak up the dye. And then they also struggle, there's definitely some difficulties with ultrasound because of the lack, the material is not homogeneous. There's a lot of different materials. The composite is multiple materials that are combined into a matrix. And so you get a lot of those acoustic barriers between the different materials. And so though there are technologies to do ultrasonics on composites, it is kind of a specialized field in that area just because of that. And so what was found is that thermography, once equipment became available, once the sensors that are used in the cameras became available, they lend themselves very well to doing composite materials. But they can be used, and you will test metal structures with them as well. So they aren't exclusive to composites. They can work on metal, and they can work on pretty much any material for that matter. Outside of aviation, thermographic inspection is used for building inspection for things like water damage. It can be used for equipment health monitoring in like factories and manufacturing environments. It can be used for electrical. You can look at the heat being given off by electrical equipment. You can judge health or condition of various electrical equipment. And so it has a broad use. It can be used for what's called gas monitoring, different gases under pressure. You can use it to find like leaks and that kind of thing, because different gases are going to have different thermal signatures. And so it can be used to find like leaks into the environment at like refining or drilling, petroleum drilling or petroleum refining facilities and that kind of thing. But for our purposes, where it's really useful in aviation, and particularly with composites, also metals, is for detecting surface and subsurface flaws. So it can see, and in fact, more subsurface flaws than anything. Usually the type of surface flaws you'd be able to see with thermography are also visible to the naked eye. So really, subsurface flaws is where it excels. It's able to do relatively large inspection areas, especially when you compare it to something like ultrasound or eddy current testing. And there's a high degree of safety. You're not using any kind of a radiation source. And what I mean by that are ionizing radiation sources, X-rays, gamma rays, ultraviolet. It does use technically heat as a radiation source, but heat is non-ionizing. It means, just heat alone, yes, it can cause burns, but it's not going to cause cancer. It's not cancer causing. Those ionizing radiations are the ones that can pass through your tissues and can cause, internal DNA reconfiguration. So no ionizing radiation sources or chemicals. Most of the time, you may need to do some cleaning, but the areas we're typically doing this on don't normally need significant cleaning. And actually, there are cases where not cleaning it can actually work to your advantage. And what I mean by that is we want a part that emits radiation, and if you have a part that normally reflects radiation, if there's a coating of dirt on it, it may actually become a better emitter than a reflector. And so you can image it better when it's dirty than when it's clean. That applies to things like fiberglass or even glass panels like windows. So some of the disadvantages, it can be affected by infrared radiation sources in the environment. Well, infrared radiation sources are things like your lights, even these LED lights we have in here. If I were to point our thermal camera at them, I'll bring the thermal camera Thursday. you'll see that they do give off a certain amount of heat. Older, when we had fluorescent and incandescent lights were more common, or what we have in some of our hangars, with the halogen lights that are in the big hangar, they give off a significant amount of heat. And so you have to be aware that that's in the environment and make sure you're taking that into account, that you're not measuring reflections from those rather than the emitted heat we're looking at. If you're outdoors, the sun is a concern. It's going to reflect off surfaces. It also has a very, very strong radiation, thermal radiation source, heat source, to the point where if you are imaging aircraft outside, you have to be careful that you don't point your camera directly at the sun for the same reason you don't look directly at the sun. It can burn the sensor out. And so please, when we're outside doing this, do not point the cameras at the sun, because there will then be black lines and spots on our cameras that are not fixable. What's that? That's all up to you. I've got some of the glasses for the eclipse coming up. I'd suggest getting some of those. A lot of libraries have them for free. What's that? April the 8th or 10th? I don't know, sometime in April. It's a Monday in April. I know it's a Monday. Electrical, if you're working near electrical equipment that can give off heat, or any other, again, there's lots of sources of heat, and you don't want that to contaminate your results. By I mean contaminate is extra heat in the environment. You have to have specialized equipment and training, just like we need for our other methods. The equipment is kind of in the medium price range, I would say. You can get a professional grade camera start in the $5,000 to $10,000 range, compared to eddy current ultrasound testers that kind of start in the $15,000 to $20,000 range. But it's obviously not as cheap as 4 cans or 3 or 4 cans of spray that are $15 a piece, $15 to $20 a piece for performing penetrant inspection. So it's kind of in the middle. It's not, and again, it's not a $60,000 or $80,000 borescope that can measure, but it's still, they start in that range. You can get thermal cameras that go upwards of hundreds of thousands of dollars that are much higher resolution or automate functions and that kind of thing. Variabilities in material emissivity and infrared reflectivity can affect your results. So you have to calibrate the camera for reflected energy and emissivity, and we'll go through that process as part of what we're learning here. It's difficult to determine size, so this is more of currently, and what we're going to be doing, the version of thermography we're going to be doing is more qualitative than quantitative, where you can kind of get size estimates, but it's harder to get actual quantitative sizes, measurements of damage. However, current developments right now, with different kinds of algorithmic processing of the heat maps, or now even using things like machine learning and things like that are starting to get more quantitative measurement systems out there. And then things that are non-uniform can hide the indications. And so what I mean by that is not necessarily, a composite is not uniform in that, it's got fibers and that kind of thing. But what I mean non-uniform is if you go from just a glass fiber sandwich area to an area that has, some kind of a core, like a honeycomb core, that's going to change what your emitted heat signal is going to look like. And so you got to be careful that you're, paying attention to if there's a larger change in the material. Are you getting an indication, or are you just picking up the change? Essentially, is it a relevant indication or is it a non-relevant indication? And if you have a non-relevant indication, is it in an area that could potentially hide a relevant indication? So not much different than what you've been doing, but you just have to be aware of what the material is like that you're working with in order to take that into account. So the functional theory, what we're looking for here is that a properly laminated or bonded material, or a material that's relatively uniform, like a metal or a composite panel that's laid up properly, they're going to have known thermal characteristics. The main ones are that we're looking at the capacitance for heat. The heat capacitance is the measurable physical quantity equal to the ratio of heat applied versus how much heat that it essentially absorbs. You know, different materials are going to absorb more or less thermal energy. So that capacitance, and then diffusivity is how quickly that energy moves through, or how well it moves through. Conductivity, how quickly it moves through. Diffusivity, how well the ability to conduct thermal energy relative to its ability to store. Okay. Any kind of disbonds, delaminations, areas where there isn't enough resin, dry spots, inclusions, those kind of things are going to have anomalous, or they're going to cause a change in the thermal signature in that area. And they can be located when conditions are correct. If if you've imaged it properly, if you've calibrated your camera for the reflected heat and the emissivity of the part or the surface, then we should be able to see those kind of things. So we can use it in a lot of different kinds of detection. Here's some examples and what they look like. So a delamination is shown there at the top. That's probably one of the most common things we're looking for. Or a void being areas where you didn't get like resin penetration. Impact damage, which causes delamination. You can use it during, after a layup's been done to verify fiber orientations. You can actually see the fibers going in different directions throughout the layers with certain imaging capabilities. Here's the disbonding. This right here is like a honeycomb core, and you can see the differences in, they say, glue or epoxy. Some areas have more, are conducting heat better, others are conducting heat worse, which gives you some relative idea of how well that epoxy was spread throughout that honeycomb core. Water ingress is another big one in aviation. That's water that makes its way between layers or into a composite structure. And then what's the problem with water inside of a composite structure? There's a couple. What? It doesn't really eat at it so much. It's not corrosive per se. It can what? How does it move around? When it freezes, you get up into altitude, the water that's gotten between layers or into pockets freezes, and then it gets bigger. It expands and causes even more delamination to occur. What else about water is a problem? It could cause microbial growth. What's a big thing in an aircraft that we have to be concerned about? Weight. It's heavier, right? Water's heavy, right? If there's not supposed to be water inside of a panel or between layers, it's going to cause weight. You'd be amazed at how much weight airplanes gain. We'll talk about it this summer in summer servicing. But we'd weigh the airplanes, they'd get significantly heavier, measurably heavier. Most of the weight we were finding was due to dust and skin cells and all the other crap that comes off of people and ends up packed all in the areas of the fuselage. Yes, that's a pretty picture. I know I'm seeing a lot of gross faces. Insides of passenger airplanes are disgusting, by the way. So spot welds, we can look at things like welds, metal, disbonding, if you've got a bonded metal. Corrosion, you can actually find corrosion in a riveted structure. It's more difficult, I think, than using eddy current to do that, but it is doable. And you can typically scan a larger area. Contamination, here's an example of fluid level. Those are basically pop cans. One's full, the other one's half full. Okay. I like to be optimistic about it. Right, this one's half full here. Again, I'm being optimistic about it. So I assume this is a bottling line where they're filling them. Hopefully, it's probably something like that, and they're checking fill level on a bottling line. So here's some general terminology. I've thrown some of these words out. You may or may not have caught the meaning of them. But heat is a form of energy transferred by difference in temperature. What is heat? When you had physics, high school physics, what did they describe heat as? What's that? It's what? Particle motion, right? The more heat there is, it's a measure of particle motion. The faster and the more the particles are moving in an object, the higher its heat. And so we can add heat, we can add that energy, or we can take that energy away. Temperature, measurement of that average kinetic energy of the molecules or atoms in an object or system. So that's that. Black body, this is something that's used for camera calibration. This is a perfect absorber and then subsequent emitter of radiation. What it means is this is something that does not reflect heat. Okay? And reflecting heat is different than reflecting visible light. You know, it's infrared, it's part of the electromagnetic spectrum. These are larger wavelengths than visible light. They're longer wavelengths, infrared, ultraviolet's on the shorter wavelength side. Longer wavelength, right? Lower frequency than visible light. But a material can be a absorber or a reflector. So an example that I like to use is glass. The glass, these windows, for instance, these do not absorb, let me think. These do not absorb visible light, right? We can see through the window, right? Visible light passes through, but plate glass, like a window, is a really, really good reflector of infrared light, heat. Okay, that's why, so you can see through it, but a thermal camera cannot. So a black body is a total absorber. It has minimal reflection. Emissivity is probably the most important term you're going to need to know for thermography. And that is, and this ties into that black body, a black body where I say it absorbs heat and then re-emits it, all heat, it doesn't have any kind of heat reflection. That is it has perfect emissivity. It has an emissivity of 1. Basically, it absorbs 100% of the infrared energy that hits it. It does not reflect any of that, but it does give it back off again. The object gets warm, and you would essentially it would feel warm to the touch. So the ratio of the actual amount of radiation that is emitted, now we can't see the light that's being absorbed or the heat being absorbed, but we can see it when it comes back out, not bouncing off the surface, but rather comes back out. And so that's where it's also known as a perfect emitter. So the amount of radiation that's emitted versus that black body, and that black body is 100% or 1.0. Anything that's not a perfect emitter is less than that. The standard we use is 3M electrical tape. That seems really odd, but 3M black electrical tape has a emissivity of 0.95. And that's a convenient, easy to carry, known emissivity that we can place on a material and then make a comparison to figure out what it is for a given material. So in general, the duller and blacker the material, the closer its emissivity is to 1. However, remember, dull and black, looking at something, is visible light. And we are working in the infrared spectrum, so things do behave differently. And again, that glass example is it transmits visible light, but it reflects infrared light. Reflectivity, the amount of infrared, this is infrared reflectivity, radiation that bounces off a surface. Okay? The glass over here is a very good infrared reflector. It reflects most of the infrared light that hits it, or infrared energy. It is a very poor visible light reflector, unless you put something right behind it and turn it into a mirror. Okay? But without anything behind the glass, it appears as a mirror when you use a thermal camera. You can actually see your heat reflection in the glass. If you point it straight at the thing, you will see an outline of your body in the glass, and it is your heat hitting the glass and bouncing back to the camera. What do you mean? Oh, a mirror is basically a piece of glass with a dark surface right behind it. And then it becomes a visible light reflector. But, and it would also be a thermal reflector at that point too. It's always going to reflect thermal. So emissivity and reflectivity are inverse. Something that has a high emissivity has a very low reflectivity in the infrared range. Okay, so if you have a perfect emitter, something that absorbs energy and then re-emits it, like that black body, it's going to be highly emissive. It's going to be 100% emissive. It's not going to reflect any heat. Now there's things that are close, but there's nothing that's perfect. The ones they use for camera calibration are like 0.9999% emissive, something like that. I mean, in theory, there's a tiny, tiny amount of reflection, but you can't even measure it. Reflectivity, again, the amount of heat that bounces off. So glass would have a low emissivity, a high reflectivity. Okay. Thermal conductivity, the ability of a material to internally transfer heat, whether that's coming into a surface, moving around in it, and then coming back out the same surface. Again, it's not a reflection. It's not the heat bouncing off. It's the heat going in, being absorbed, and then being re-emitted, coming back out. Or you can think of it as heat's put on one side of a surface and it transmits to the other side. It works its way through. Diffusivity refers to that, how fast that heat transfers through an object. And that's directly related to the conductivity. A material that's highly conductive of heat is going to diffuse quickly. It's going to have a high diffusivity. A material that is not a good conductor of heat, an insulator, is going to have a low diffusivity. It's going to slow the speed of heat transfer. How many of you know we have a space shuttle tile sitting out in the foyer out here? If you want to see a space shuttle tile, there's one out in the foyer. That has an extremely low diffusivity rate, right? We don't want that heat during reentry to make its way from the outside of the spacecraft to the inside. And so it's going to prevent that heat from diffusing in. It also, it can absorb a huge amount of heat without heating up itself. I can't remember exactly how it works, but. So here is that electromagnetic spectrum that we've looked at. And infrared is the long wavelength, low frequency. Now frequency, this is showing in wavelength, right? So short wavelengths to the left, long wavelengths to the right. That means that high frequency is on the left, low frequency is on the right, okay? And so we are looking in this area that is just a bit longer than visible light. You can see the visible spectrum is very small compared to the infrared spectrum. So the infrared spectrum is going anywhere from 0.75 nanometers to 1 millimeter. So here's 0.75 nanometers up to about, I've got a little bit less, 1 millimeter. Then this is a logarithmic scale. So if you're looking at it a little confused, remember it's a logarithmic scale, not a linear scale. The specific range we're going to look at with infrared cameras is, they actually come in two ranges. We are going to be looking in the 7.5 to 14 micrometer range, which is known as long wave infrared. There are cameras designed to work in the mid wave, which is 3 to 5 micrometers. That's those ones used for gas imaging. That's what I was telling you. You're able to find leaks from tanks and that kind of thing. That's where you can see the thermal differences between gases. But for solid objects, we're going to be in the 7.5 to 14 micrometer range there. When we perform thermography, there are three basic steps we have to perform. The first is we have to do something called excitation or stimulation. This is, we need to change the temperature of an object. Okay? And it can be either heating up or cooling down. It basically means the temperature can't stay constant. We need to see it over time. When you're imaging, you're going to take images over a period of time, and you're going to look at how they compare. Okay. We're going to measure temperature. Essentially, what a thermal camera is it takes, you'll see an image. When you look at the images, you saw those images earlier with all those different colors in them, right? Those are the camera is taking essentially a big grid of temperatures. Essentially, it measures the temperature in thousands or hundreds of thousands or millions of spots simultaneously. What you're seeing in those visible images is then the camera overlays colors for specific temperature ranges for each pixel or each spot. But the camera itself, it's like a big grid. It's like a giant Excel spreadsheet of temperatures that it takes all simultaneously. I mean, I've used the heat guns. You pull the little trigger, take a temperature. Okay, so our camera that's 250,000 pixels is like taking 250,000 of those little heat guns and all pointing them at spots next to each other at the same time. That's essentially what a thermal camera is. And then we have to analyze what we've seen, take an analysis. So how does this work? So if we break it down a little bit more, in the stimulation step, that's roughly broken into two areas, passive and active. Okay, we'll talk about what those mean. Measurement, that's pretty much infrared cameras. Could be mid-wave, could be long wave, but we're using long wave. And then we do our analysis, and we can either do raw analysis, direct viewing of the image, which for us means oftentimes putting a color gradient over top of it. Because if you got a giant grid that's full of numbers and you're trying to look at 250,000 numbers, you're probably not going to be able to see much besides your eyes crossing, right? So the camera or our software we're using puts a nice color kind of thing over it. But a computer, an algorithm, machine learning, AI can take a look at, can actually look at all those numbers and look for things like trends and things like that in them. And so that's a processed analyzation. So what I mean by passive versus active, passive is using things in the environment as our excitation source, as our heat source. Okay. Here I've got things like solar and ambient. Active is when we actually heat the specific area that we're going to be looking at with something we use. Optical, direct contact, forced convection. That's the drying oven that we use for liquid penetrant. That's a convection oven, moving hot air, moving warm air. Electromagnetic induction, using that's the heating that occurs in the mag bench when you hold the process button too long, which a few of you did do on the exam, by the way. I heard some buzzing going on in there for way longer than it needed to. Remember, it's like, that's about all you need, not, that kind of worries me when I hear that. If we were doing electromagnetic induction heating, then you're in the right direction, but that's not designed for doing that. Okay, that's not an induction furnace. I've worked with induction furnaces. They're a lot bigger than that. And they get things a lot hotter than that. Okay. I'm going to skip over the, so the excitation examples, passive. We tend to use passive excitation more in a qualitative analysis. So checking for the presence of things. Do we have delamination? Do we have water ingress? Do we have ice? Trapped water is water ingress. Do we have ice? What's the underlying structure, general condition of it? Compared to active is more quantitative. This is measuring size, area, depth, the extent of, and this is you can look for, is there delamination qualitatively? How big of an area is delaminated? That's quantitative. You can do some of that passively. You can do some of that yourself. But if you really, really want to get precise, you need to use active heating and you need to use some kind of a analysis tool. Impact damage, foreign objects, fluid ice inclusion, again, measuring versus Nothing. Here's the camera. Here's what one of the cameras looked like. Okay. This is our bigger camera. Here's an image taken by a thermal camera of an aircraft. What do you see in this image? Now, you don't have the scale. You don't know what the colors necessarily mean. What do you think the colors mean in this image? And what do you see? Corey? Yep, so this one, red tends to be the hottest, or pink is actually the warmest. Blue, purple is the coldest. Okay, and then it kind of goes green to yellow. Okay, purple, blue, green, yellow, and getting into orange, red, and pink. Okay, so that's a pretty standard scale, but you can change what this looks like. This camera right here, it shows what the scale is over here. So you can see it's more purple down here at the bottom of the bar. It goes up to white. White is actually the hottest, oftentimes. Okay, what else can you see about this? Just, I know you haven't learned what these are, but I'm sure you've seen these kind of images before. They're common on TV. They're common if you watch anything, military shows or police shows, right? You see them facing the bad guy running away with a thermal. What's that? Well, this is a FLIR camera. Yeah, it's a FLIR. So if you've worked with the FLIR stuff in the military, that's exactly what this is. So anything here? What do you see on this? What do you think you see here? Just, you haven't learned anything about it, but what kind of things can you tell me about this picture? It's an airplane. Okay, we got that. If you know the window sweep, you might be able to tell me if it's a Boeing or an Airbus or whatever, but Dugan. Well, what are the rows of rivets doing? Why do we have a bunch of rows of rivets on the aircraft? To hold what together? We got skin attached to what? These are like stringers, formers, bulkheads. Okay, that's the underlying structure where those rivets are. Okay, so you can see the grid that makes up the structure below the airframe. You're going to do this on one of the airplanes in the lab. You had something, Corey, or was it the same thing? No. What else can you see? You had a pitot tube there. Now isn't pitot usually hot? So is it on right now? Nope, it's off. It's actually cold. I'll tell you why. Pitot tubes are typically what? What are they made out of? Bare metal. Bare metal is a good reflector of heat. That is actually reflecting probably the sky. Okay? Not sky, but the sky, right? If it was reflecting sky, it would be hot. It would be, okay, if it was reflecting sky, it would show a heat signature. There we go. That's the better way to put it like that. Yeah, okay. What else do you see? So knowing that that's a reflection of the sky, what else might be a reflection of the sky? I'm gonna make sure I use the word the. What? The windows. Remember I said glass is a really good reflector of heat? That's reflecting the sky. And this is the sky above it here to the left. Top left, right? It's cold. As long as you don't point the camera at the sun, the rest of the sky is really cold, right? Space is cold. You look through the atmosphere, you see space, it's cold. Okay, the atmosphere holds in a certain amount of heat, but not tons of it. It's getting to be a better reflector of heat, we're learning, but okay, anything else? Green circle right here. Probably is a static port, probably is the structure behind, the doubler behind the static port. The static port itself is going to be very tiny in the center. There's kind of a cool spot right in the center. Okay. The other thing I'll tell you, what's right behind, so this is where the pilots sit, right? What's right behind the pilots in our 727 out there? Now ours has, what's that? Engineer's panel or circuit breaker panel, and what's in there? Bunch of wires and electrical. What do we have with wires and electrical? They give off heat because of the resistance, and so that's why you've got a hot spot there. That's kind of where the electrical bay down here. So the plane was probably on recently. It's been shut off. The pitot heat and the static heat is cool. The windshield heat is not on, but it's obviously been powered up at some point. because all the areas that would get warm are warm still. Okay. So here's some examples, raw direct viewing of the top here. We can see, yeah, can's got some liquid in it. It's about half full. If you wanted to do something down here, we could process like this. This is that that image of the honeycomb structure, and we're looking at like how much epoxy is in all the different cells. And we could run processing on here to give us some kind of percentage of fill in each area, or relative percentage of fill in each area. You know, are there areas where we didn't get enough epoxy? Do we have pockets or dry spots or voids that shouldn't be there? And if you have the correct type of, you know, ways of doing that, you could. So processed imaging here, things called lock-in, component analysis, pulse phase, and then, you know, the other part of that is now moving into using just someone had an awesome article in their outline about the uses of AI and machine learning in NDT. Which group was that? I even put a note on there. I don't know, someone had a really good article about it that I thought was super interesting. So our analysis, what we're going to do in aviation, raw, qualitative, and probably the most common is looking for these two right here, the trapped water and ice and the delamination. That's what manufacturers today are specifying. The big manufacturers, Boeing, Airbus, Bombardier, Mitsubishi, Embraer, these are the kind of things they're specifying, using it to find trapped water and ice and delamination. On the manufacturing side, they're using it for things, you know, more qualitative and you know, computer-based measurement for things like thickness and depth, adhesion, automated detection. You can do automated detection for quality assurance, quality control when you're laying up composites. You can also use automated detection to make sure that you know that it's bonded properly. You can also make sure that you don't have contaminants in there, that you didn't accidentally laminate in a chunk of plastic, you know, that fell off of one of your machines, right? Material characteristics, you know, that's kind of on the development, R&D, research and design side, research and development side. Okay. So thermography is known as an indirect process. And what that means is that the energy is actually absorbed by the part, and then we're going to look at it as it comes back, as it works its way back to the surface. So that's in contrast to like ultrasonic testing, which is a direct process. Okay, the energy is injected into the part, and we're looking at it that same energy as it's released immediately or after it passes through the object. It isn't changed by the object in any way. So infrared energy, when it's traveling through the air, it's a wave, right? It's an energy wave. When it hits the object, it turns into motion of the particles. Right? How many of you have been underneath infrared heaters? You've probably seen them at the patio at the bar, those little mushroom-shaped things or the long things. You stand under them, your skin feels warm. Those are infrared heaters. You can't feel that heat in the air, but you feel the heat. Once it touches your skin, it warms your skin up without actually warming the air around you. Now your skin's going to radiate some heat back off and warm the air, but as it passes through the air, it's not actually warming the air. Okay? That's what indirect means. Versus a direct process, you know, we're looking at the sound wave. The sound wave is the motion, the physical movement of the particles, not how fast the particles themselves are spinning, the electrons are spinning, you know, the motion inside the atom. It's the motion of the atom as a whole, right? Moving back and forth. Or, you know, radiography, we use ionizing radiation. It passes through the part. When you x-ray something, it doesn't get hot, right? The energy just passes through it to the other side. So it doesn't cause an energy change in the part itself, okay? So you're measuring that energy directly. Okay? Here's what I mean by that being indirect, okay? So this is an image of what happens. So infrared, what's called incident shortwave energy, that's the fancy name for saying infrared, is going to come down, it's going to strike the part. A certain amount of it is going to reflect off the surface. We don't care about the reflection. We don't want to measure that. A certain amount of it, of some materials, is going to transmit through. Most material, air allows a lot to transmit through. Most materials are either going to reflect or absorb the energy. And then the energy that gets absorbed is going to increase that, movement of the particles inside the individual atoms and increase the heat. And then that energy is going to diffuse back out of the part, and it's going to be emitted. That's the heat you can feel when you touch a part, or that's the heat that our camera is able to see when we image it. Camera can also see the reflected heat, and we don't want to pick that up. We want to try to minimize that as much as possible. All we want to image is the emitted stuff. And if you're looking at passing through, you don't want to see it pass through. Now, next time when I bring this up, I'm going to draw a slightly different version of this where we show if the heat source is on the opposite side, but you can actually see, you really don't need to. You can see we could image this object from above, and we could pick up this heat that's accumulating, or we could image it from the back side. So the heat source doesn't necessarily have to be on the same side as the camera. We just have to be aware if we're imaging it from up here, the same side as we don't want any reflected heat. If we're imaging it from down here, most materials don't transmit infrared energy directly. They're going to absorb it, turn it into heat, and then that heat's going to be emitted. But if you do have a material that for some reason does transmit infrared, you would have to take that into account. Again, very few materials. The lens on the thermal camera allows transmission of infrared, germanium oxide, and we'll look at that. So let's stop there.